Hello guys, welcome back to my channel. Today we will be exploring a very influential paper called LoRA. LoRA stands for Low Rank Adaptation of Large Language Models. And it's a very influential paper. It came out I think 2 years ago from Microsoft. And we will see, in this video, we will see what is LoRA, how does it work, and we will also implement it in PyTorch from zero without using any external libraries except for Torch, of course. And let's go. So we are in the domain of language models, but actually LoRA can be applied to any kind of model. And in fact, in my demo that I will also show you later, we will apply it to a very simple classification task. And so before we study LoRA, we need to understand why we need LoRA in the first place. So let's review some basics about neural networks. So imagine we have some input, which could be one number or it could be a vector of numbers. And then we have some hidden layer in a neural network, which is usually represented by a matrix. But here I show you the graphical representation. And then we have another hidden layer. And finally, we have the output, right? Usually, when we train a network, we also have a target. And what we do is we compare the output and the target to produce a loss. And finally, we backpropagate the loss to each of the weights of all the layers. So in this case, for example, we may have many weights. In this layer, we will have a weights matrix and a bias matrix. And each of these weights will be modified by the loss function. And also here, we will have a weight and a bias matrix here. Now, what is fine-tuning? Fine-tuning basically means that we have a pre-trained model and we want to fine-tune it on some other data that the original model may have not seen. For example, imagine we work for a company that has built its own database. So this new database has its own SQL language, right? And we have downloaded a pre-trained model, let's say GPT, that was trained on a lot of programming languages, but we want to fine-tune it on our own SQL language so that it can answer so that the model can help our users build queries for our database. And what we used to do is we train this model with this entire model here on new data, and we alter all these weights using the new data. However, this creates some problem. The problem with full fine-tuning is that we must train the full network, which first of all is computationally expensive for the average user, because you need to load all the language in the memory, then you need to run back propagation on all the weights. Plus, the storage requirements for the checkpoints are expensive, because for every checkpoint, for every epoch, usually we save a checkpoint and we save it on the disk. Plus, if we save also the optimizer state, let's say we are using Adam optimizer for each of the weights keeps also some statistics to better optimize the models. So we are saving a lot of data. And if we suppose we want to use the same base model but fine-tuned on two different data sets, so we will have basically two different fine-tuned models. If we need to switch between them, it's very expensive because we need to unload the previous model and then load again all the weights of the other fine-tuned model. So we need to replace all the weights matrix of the model. However, we have a better solution to these problems with LoRA. In LoRa, there is this difference. So we start with an input and we have our pre-trained model. So we want to fine-tune it, right? So we have our pre-trained model with its weights and we freeze them. Basically, we tell PyTorch to never touch these weights, just use them as read only, never run back propagation on these weights. Then we create two other matrices, one for each of the metrics that we want to train. So basically in LoRa, we don't have to create matrices, the matrices B and A for each of the layers of the original model. We can just do it for some layers, and we will see later how. But in this case, suppose we only have one layer and we introduce the matrix B and A. So what's the difference between this matrix B and A and the original matrix W? First of all, let's look at the dimension. The original matrix was D by K. Suppose D is let's say 1000 and k is equal to 5000, we want to create two new matrices that when multiplied together they produce the same dimension, so d by k. So in fact we can see it here, d by r when it's multiplied by r by k will produce a new matrix that is d by k, because the inner dimensions cancel out. And we want r to be much smaller than d or k. We may as well choose r equal to 1. So if we choose r equal to 1, basically we will have a matrix that is d by 1, so 1000 by 1, and another matrix that is 1 by 5000. And if we compare the numbers of parameters in this matrix, in the original matrix W, we have the number of parameters, let's call it P, is equal to d multiplied by k, which is equal to 5 million numbers in this matrix. In this case, however, we have two matrices, so if r is 1, we will have one matrix that is d by r, so 1000, plus 5000. Only 6000 numbers in this combined matrix. But with the advantage that when we multiply them together, we will still produce a matrix of d by k. Of course, you may think that this matrix will not capture the same information as the original matrix W because it's much smaller, right? Even if they produce the same dimension, they actually have it's a smaller representation of something, so you lose some information. But this is the whole idea behind LoRA. Actually, the whole idea behind LoRA is that the matrix W contains a lot of weights, a lot of numbers that are actually not meaningful for our purpose. They are actually not adding any information to the model. They are just a combination of the other weights. So they are kind of redundant. So we don't need the whole matrix W. We can create a lower representation of this W and fine-tune that one. So let's continue with our journey of this model. Let me delete the ink. Okay, so we create these two matrices, B and A. What we do is we combine them because we can sum them, right? Because they have the same dimension. When we multiply B by A, it will have the dimension D by K. So we can sum it with the original W. We produce the output, and then we have our usual target. We calculate the loss, and we only backpropagate the loss to the matrix that we want to train. That is the B and the A matrix. So we never touch the W matrix. So our original model, which was the pre-trained model, is frozen, and we never touch its weights. We only modify the B and A matrix. So what are the benefits? First of all, as we saw before, we have less parameters to train and store, because in the case I showed before, we have, for example, 5 million parameters in the W matrix in the original one, and using R equal to 5, we only have 30,000 parameters in total, so less than 1% of the original. Less parameters also means that we have less storage requirements and faster backpropagation, because we don't need to evaluate the gradient for most of the parameters. And we can easily switch between two fine-tuned models, because, for example, imagine we have two different models, one for SQL and one for generating JavaScript code. We only need to reload these two matrices if we want to switch between them. We don't need to reload the W matrix because it was never touched, so it's still the same as the original pre-trained model. Why does this work? So the idea is that, and it's written in the paper, is that the pre-trained model they saw, the intuition is that they have an intrinsic dimension that is smaller than their actual dimension. And inspired by this, they hypothesized that the updates to the weights also have a low intrinsic rank during adaptation. And the rank of a matrix basically means it's, we will see it later with a practical example. Basically it means, imagine we have a matrix made of many vectors, column vectors, and the rank of the matrix is the number of the vectors that are linearly independent from each other. So you cannot combine linearly any of them to produce another one. This also indicates kind of how many columns are redundant, because they can be obtained by linearly combining the other ones. And what they mean in this paper is that the W matrix actually is rank deficient. It means that it does not have full rank. So it has a dimension maybe 1000 by 1000, but maybe the actual rank is, let's say, 10. So actually we can use a 10 by 10 matrix to capture most of the information. And the idea between this rank reduction is used in a lot of scenarios, also, for example, in compression algorithms. So let's review some mathematics of ranking and metric decomposition, and then we check the LoRA implementation in PyTorch. So let's switch here. Let's go here first. So I will show you a very simple example of matrix decomposition and how a matrix can be rank deficient, and how we can produce a smaller matrix that captures most of the information. So let's start by importing the very simple libraries, Torch and NumPy. Then I will create a 10 by 10 matrix here that is artificially rank deficient. So I create it in such a way that it is rank deficient with a actual rank of 2. So even if this matrix is 10 by 10, we can see that it has 100 numbers. The rank of this matrix is actually 2, and we can evaluate that using NumPy. So we will see that the rank of this matrix is actually 2. This means that we can decompose it using an algorithm called SVD, which means singular value decomposition, which produces 3 matrices U, S, and V that when multiplied together they give us W. But the dimension of this U, S, and V can be much smaller based on the rank. So basically it produces 3 matrices that if we take only the first R columns of these matrices, where R indicates the rank of the original matrix, they will capture most of the information of the original matrix. And we can visualize that in a simple way. What we do is we calculate the B and the A matrix just like in the LoRA case using this decomposition, and we can see that we created the lower representation of the W matrix, which is originally was 10 by 10, but now we created 2 matrices, one B and one A, that is 10 by 2 and 2 by 10. And what we do is we take some input, let's call it X, and some bias, and it's random. We compute the output using the W original matrix, which was the 10 by 10 matrix. So we multiplied by X, we add the bias, and we also compute the output using the B and A matrix, that is the result of the decomposition. So we calculate Y prime using B multiplied by A, just like LoRA, multiplied by X plus bias. And we see that the output is the same, even if B and A actually have much less elements. So in this case I renamed the, well, I forgot to change the names. This is B and A, okay. B and A, and what's okay. So what I want to show, and this is not a proof because I actually created artificially this W matrix and I made it rank deficient artificially. I actually took this code from somewhere, I don't remember where. And so the idea is that we can have a smaller matrix that can produce the same output for the same given input, but by using much less numbers, much less parameters. So as you can see, the B and A elements combined, the number of elements in the B matrix and the A matrix combined are 40, while in the original matrix we had 100 elements. And they still produce the same output for the same given input, which means that B and A captured most of the information, the most important information of W. Now let's go to LoRA. So let's implement LoRA step by step. What we will do is we will do a classification task. So imagine we have a very simple neural network for classifying MNIST digits, and we want to fine-tune it on one specific digit because we see that the performance on one specific digit is not very good, so we want to fine-tune it on only one. And we will use LoRA and show that when we fine-tune with LoRA, we are actually modifying a very small number of parameters, and we only need to save very small number of parameters compared to the pre-trained model. Let's start. So we import the usual libraries, so Torch and matplotlib. Actually, we will not need it, and TQDM for visualizing the progress bar. We make it deterministic, so it's always returns the same results. And we load MNIST, the dataset. It's already integrated into Torch Vision, so it's not a big deal. And we create the loader. We create a very unoptimized neural network for classifying these digits. So basically, this is a very big network for the task. We don't need such a big network, but I want to make it specific. I made it on purpose such big because I want to show the savings in parameters that we get. So I call it rich boy net. So because daddy got money, so I don't care about efficiency, right? And it's a very simple network made of 3 linear layers. And with a ReLU activation, and the final layer is just basically the classification of the digit into one of its categories, 0, 1, or 2, or up to 9. So we create this network and we train it on MNIST. So we run for only one epoch and we train it, just simple training of MNIST for classification. And then what we do is we keep a copy of the original weights because we will need it later to prove that the LoRa didn't modify the original weights. So the weights of the original pre-trained model will not be altered by LoRa. We can also test the model, the pre-trained model. We can test it on and check what is the accuracy. So if we test it, we can see the accuracy is very high. But we can see that for the digit number 9, the accuracy is not as good as the other digits. So maybe we want to fine-tune, especially on the digit 9. Okay, LoRa actually in the paper was fine-tuned on large language models, which I cannot do because I don't have the computational resources. So that's why I'm using MNIST and this very simple example. Anyway, so we have one digit that we want to fine-tune better, right? Let's visualize, before we do any fine-tuning, how many parameters we have in this network that we created here, this network here, rich boy net. So we have, in the layer 1, we have this matrix weights and this bias. This weights for the layer 2 and this bias. This weights matrix for the layer 3 and this bias. In total, we have 2,807,010 parameters. Now, let's introduce LoRa. So as we saw before, LoRa introduces two matrices called A and B, and the size of these matrices is if the original weights is D by K, the B is D by R, and A is R by K. So I just call it features in and features out. In the paper, it's written that they initialize the B matrix with 0 and the A matrix with random Gaussian initialization. And this is what I do here as well. Then they also introduce a scale parameter. This is from the section 4.1 of the paper, that basically allows to change the rank without changing the scale of the items. And I just use alpha. Alpha is fixed. Because maybe you want to try the same model on different ranks, so instead of the scale allow us to keep the scale of the numbers the same. If LoRa is enabled, we want the weights matrix, so we will basically run LoRa only on the weights matrix, not on the bias, because also in the paper they don't do it for the bias matrix, only on the weights. So if LoRa is enabled, the weights matrix will be X, so the original weights, plus B multiplied by A, just like in the paper, multiplied by the scale. This is also introduced by the paper. So basically, instead of multiplying this should be W. Instead of multiplying X by W, just like in the original network, we multiply it by W plus B multiplied by A. And this is written in the paper. We can see it here. Let's go down. It's written here. So instead of multiplying X only by W, we multiplied by this delta W, which is how much the weights have moved because of the fine-tuning, which is B by A. And this is what we are doing here. And we add this parameterization to our network. So to add this parameterization, I'm using a special function of PyTorch called PyTorch parameterization. So if you want to have more information how it works, this is the link, but I will briefly introduce it. Parameterization basically means allow us to replace the weights matrix of the linear 1 layer in this case with this function. So every time the neural network wants to access the weights layer, the weights matrix, it will not access directly the weights matrix, it will access this function. And when this function is what? Is basically our LoRA parameterization. So when it will ask for the weights matrix, it will call this function, giving us the original weights. And we just alter the original weights by introducing the B and A matrix. So when it will multiply the PyTorch will keep doing its work, so it will just multiply the W, so the weights, by X, but actually the weights will be the original weights plus the B and A that we combined in this way according to the paper. And we can easily enable or disable LoRA in each of the layers by modifying the enabled property. We can see it here. So if it's enabled, we will use the B and A matrix. If it's disabled, we will only use the original weights. If we enable, basically it means that we enable also the fine-tuned weights. If we disable it, the model should behave just like the pre-trained model. And we can also visualize the parameters added by LoRA. So how many parameters were added? Well, in the original layer 1, 2, and 3, we only had the weights and the bias. Now we also have the LoRa A matrix and the LoRa B matrix, and I chose a rank of 1. And this I defined it here, rank of 1. And so the matrix B is 1000 by 1 because the weight matrix is 1000 by 784. So 1000 by 1 multiplied by 1 by 784 gives you the same dimension of the weights matrix. And we do it for all the layers. So in the original model without LoRa, we had 2,807,010 parameters. By adding the LoRa matrices, we have 2,813,804 parameters, but the only 6,000 of them, so the one introduced by LoRa, will be actually trained. All the others will not be trained. And to do it, we freeze the non-LoRa parameters. So we can see here, I created the code to freeze the parameters. So we just set requires grad equal false for them. And then what we do is we fine-tune the model only on the digit 9, because originally, as I show you here, we want to improve the accuracy of the digit 9. So we don't fine-tune it on any other thing. So we have a pre-trained model that was trained on all the digits, but now we will fine-tune it only on the digit 9, hoping that it will improve the accuracy of the digit 9, maybe decreasing the accuracy of the other digits. So let's go back here. I fine-tune this model only on the digits 9, and I do it for only 100 batches because I don't want to alter the model too much. So I do it with the training, it is very fast, and then basically I want to show you that the frozen parameters are still unchanged by the fine-tuning. So the frozen parameters are this one, and they are still the same as the original weights that we saved after pre-training our model here. So here we save the original parameters. We actually clone them so they don't get altered. And we can see that they are still the same. And then what we do is we enable LoRa, and we see that the weights, so when we access the weights, PyTorch will actually replace the weights by the original weights plus B multiplied by A multiplied by the scale according to the formula that we have defined here. So every time PyTorch tries to access the weight matrix, it will actually run this function, and this function will return the original weights plus B multiplied by A multiplied by the scale. And this is what is happening here if we enable LoRa. If we disable LoRa, we are disabling the parameterization, so it will just return the original weights. And why does this happen? Because here we said that when LoRa is disabled, just return the original weights. And so what we can do now is that we can enable LoRa and test the model. And we can see that now the digit 9 is performing much better. But of course we lost some information about the other digits. And if we disable LoRa, the model will behave exactly the same as the pre-trained model, so without any fine-tuning. And we can see these numbers are the same as the pre-trained model here. So the number 0 had a round count for 33, the round count for the digit line was 107, and it's the same as this one. So when we disable LoRA, the model will behave exactly the same as the pre-trained model. When we enable LoRA, we introduce the matrix B and A that make the model behave like the fine-tuned one. And the best thing about LoRA is that we didn't alter the original weights, and the only weights that we altered are the B and the A matrix, and their dimension is much smaller compared to the W matrix. So now if we want to save this fine-tuned model, we only need to save this 6,794 numbers instead of 2 million, etc. We can fine-tune many versions of this model, and we can easily switch between them just by changing the B and the W matrix in this parameterization. We don't need to reload again all the W matrix of the original pre-trained model. And this is the power of LoRA. I hope my video was clear, because I try to make videos that are theoretical but also practical. Please let me know in the comments if there is something that you want to be explained a little better. You can use my repository. It's PyTorch LoRA on my account, and you can play with it, and you can try to use different sizes of their ranking, or you can different models. It's very easy. I suggest you also read the parameterization, this parameterization function of PyTorch, because it's very easy to introduce a different kind of parameterization and also play with the parameterization of a neural network. Thank you again for listening, and I hope you enjoyed the video, and please come back to my channel for more videos about machine learning and deep learning.